Hello, my name is Jung Kim. I'm a professor at the School of Electrical Engineering at Korea University. Today, I would like to introduce my work that is called Markov decision policies for dynamic video delivery in wireless caching networks. So actually, this work was jointly by Professor Min-seok Choi at Jeju National University, Professor Albert No at Hongik University, and lastly, Professor Ming-Yu Ji at the University of Utah. So here we're gonna talk about Markov decision process, and that is the application of the Markov decision process to dynamic video delivery in caching networks. So here we nowadays we have a lot of applications that is related to on-demand video streaming. So in wireless caching network, on-demand video streaming is very important because we need to cache some contents in order to minimize the delay or stall events. So as a motivation of wireless caching, we have to think about the major application that is called on-demand streaming service. So here, as I told you before, the main key issue in on-demand video streaming is low delay or minimization of stall events. So we are saying that is called real-time service. So based on the paper written by YouTube, there are two major characteristics in streaming services. The first one is that some videos which those are very popular in worldwide takes a lot of traffic. So there are a lot of videos within YouTube. Among the videos, several videos takes very high popularity or high traffic. So it means that the users are requesting the same file frequently because those are very popular nowadays. In addition to that, usually users are very sensitive in terms of the stall events. If we feel some discontinuity during the playback, then the users will feel the unsatisfaction. But if we have some performance degradation or quality degradation in frames, that is reasonably fine. So it means that when you play back one video, if it has some discontinuity in terms of the play, then users will not satisfy with the quality. However, suppose that the video is quite seamless, whereas several frames has some low quality, that is fine. Okay. In summary, I can tell you that a relatively small number of popular contents are required at ultra high rate. This is the paper by YouTube in 2013. And next, playback delay is often the most important measure of goodness to the user than the other usual performance metrics like video quality. So in order to handle these issues, we are thinking about wireless caching networks. So with wireless caching networks, we can minimize the discontinuity or playback delay. And in addition to that, we can cache some video. Those are popularly or majorly requested by the users. Then we can make some robust or reliable networks which can provide on-demand robust streaming services. So background here, I would like to introduce the major architecture of wireless caching networks. In wireless caching networks, basically we have caching nodes. So here, this is a base station. You can see the base station in the middle of the figure. And then you can see some several storages. Those are called wireless caching. And then we have several mobile cell phones. Okay, so we have motivation as follows. A relatively small number of popular contents are requested at ultra high rate. And then bring the contents close to users. So then it means that popular video files can be cached in base stations, relays, and devices. Then we have to think about how to cache the files. Okay. So after that, reducing the duplicate contents transmission between caching node and base stations and allowing users to access to the favoring nodes with caching ability. So in this case, our question is that how to choose the node for file request. So in this case, we have to do some cache selection. Okay. So here, we want to summarize the major objective or research goals for this presentation for this for this research. So the goal is that we want to do dynamic node association and quality chunk selection for the video delivery depending on network topology and channel queue state information. So as you can see below, our streaming user is moving in a certain direction and caching nodes are already distributed. Or caching nodes are moving, but the user location is fixed. That is our basic assumption. Okay. And then user denotes the node association for every time t, and channel varies faster than time interval of node association updates. Lastly, there are several types of cache node. It means that each type of cache node stores some quality levels. Okay, so it means that each cache can store several qualities of videos, and the videos has different sizes, even though the contents are equivalent to each other. Okay. So this one shows one hop wireless caching network. So here you can see one type 1 cache, type 2 cache, type 3 cache here. And then in left hand side you can see one figure which says that one cell phone is associating with 3 different caches. Okay. So here you can see that each user requests a certain contents and has a candidate helper set whose members cache the desired contents. The desired contents has L quality levels. Okay, and videos of different quality have different file sizes, and N sub Q denotes the file size of the quality queue in bits. And then we have to assume that we have to satisfy N sub M should be less than N sub Q for all MQ. Those belongs to L sub L and M is less than Q. Those are our basic assumption. And the type L helper can deliver the video of any quality Q. And then the Q can be on elements of set L sub L, which is the set of quality of a video, and we have L different number of qualities in these contents. Okay, and each content consists of multiple chunks having the identical size, and the user leaves the desired video chunks in sequence over time. Caching helpers of type L are modeled by independent Poisson point process in order to do some mathematical modeling. Okay, and in this Poisson point process, we have to define the intensity in order to do some mathematical analysis, and the intensity is assumed as a lambda p sub L. Okay, and our assumption is that we are thinking about noise limited environment, and we also assume that streaming users are separated enough. Okay, then in that case we can ignore a certain amount of interference impacts in wireless caching systems. So here we are designing delay sensitive delivery of contents with various quality. So here our main function is that video chunks delivered from a chosen caching nodes are accumulated into the queue. Okay, and they are waiting to be played. And queue dynamics can be modeled as follows. Here, queue of t plus 1 means the queue backlog size at time t plus 1. And then we have max. Within the max, we have queues of t minus b of t, which means that we have a certain amount of departure process b of t from current queue status q of t. And then the queue backlog size cannot be negative. That's why we are taking the maximum with 0. And then we have plus m, which means the arrival process. So as you can see in the illustration below, we have black box here, and then receiving m's of t chunks with quality q of t from caching node alpha of t. It means that we are receiving capital M of t chunks. That's why this becomes arrival process. That's why there is added to current max. Then we can derive q of t plus 1. Okay. And here we are saying that the quality of video or current chunk is q of t, and our caching node is alpha of t. Because we have to select the cache in this case, alpha of t is called a decision action. Okay, this kind of formulation is also published in JSEC 2018 and TWC 2019. So we are talking about TWC 2019. Okay. So in the left hand side of the figure in the middle, we have three different types caches. Then we have to determine what quality Q of T. We have to determine how many M of T is required. Okay. So depending on the quality, the size of chunks will be updated. Depending on the number of chunks, we have to select certain amount of chunks from the cache. Okay. And then when the quality is decided, as well as the number of chunks is also decided, and then that should be allocated to video chunk Q. And within the Q, we will get some arrivals depending on the Q of T and capital M of T. And then when we are doing the video streaming, the first chunk number 1, will be transmitted to its associated receiver. And the number 1 chunk is arrived at the receiver, and then the video streaming happens. Okay. Once number 1 chunk is playback, and then number 2 chunks should be arrived at the receiver. In that case, we can immediately play back number 2 chunks once the chunk 1 is terminated. Okay. Then we can realize the seamless streaming. Okay. That's why we need a departure process that is called playback rate B of T here. So below we have some notation here in blue colors. So maximum bound of the chunk amounts can be delivered, can be denoted by this one, right hand side. And as you can see in the gold box, chunk size of the quality Q of T can be denoted by this one, because Q of T will be some control parameter here, and the related chunk size can be denoted as a function of a capital N. That's why this is possible. Okay. So in this case, in the blue box, it's kind of maximum bound. That's why the chunk size cannot exceed this maximum bound. So the gold box is a size, and the capital M of T, which is in front of the gold box, is the number of chunk. That's why entire transmission size can be denoted as the left-hand side. Okay. So here, as you can see below in black boxes, we can see the trade-off. Okay. So we have to control the trade-off. So as you can see in the black boxes, if high quality is pursued, small number of chunks is received at the receiver. On the other hand, if many chunks are delivered, then quality should be degraded because we have to send a lot of chunks. That's why individual chunks should be small. That's why we have to compress a lot. That's why quality should be degraded. That's why we can observe the trade-off between the quality and the number of chunks. Those are transmitted. So here, the right-hand side, the Q of T can be denoted by can be defined as the number of video chunks in Q. It means that there is Q bank node size in this paper. Okay. So here, in order to design delay-sensitive delay of contents with various qualities, the smooth playback is required. As I told you before, if we can feel some discontinuity between chunks, then everybody feels unhappy. Okay, but that's why even though we compress a lot in certain amount of chunks, we have to avoid these kinds of discontinuity between playback of chunks. That's why we need smooth playback. So as you can see in this slide top, for smooth playback, user queue should not be empty, not to wait for the next chunks. That's why we have to make a condition about that. Okay, so the queue dynamics should be designed based on this philosophy. Okay, so in the middle, you can see some equation that is for the constraint for stacking many chunks enough. That's why we have to avoid the case where the queue is empty. That's why we have to put chunk as much as possible in this case. That's why, as you can see in the red characters, we are saying that constraint for stacking many chunks enough. That is our basic requirement. As you can see in gold characters, a large is constant enough to avoid queue emptiness. That's why we have to set enough large value over there, and then we have to avoid the case where the queue is empty. So we need to put a lot of chunks into the queue if possible. Okay, and then we have streaming over there. Okay, so we have so suppose that we need a playback delay over there. We have playback delay over there. Then we may feel some discontinuity between the playback. That's why we have to think about that as well. So here, in order to control the delay and quality, we need to use the Lyapunov optimization. So actually, this is not easy to understand, even though if you don't have any background in Lyapunov optimization. So here, let me introduce what is the Lyapunov optimization. So in Lyapunov optimization, if you have a lot of delays over there, then you have to solve that issue even though you have one major objective. So suppose that you want to improve the quality, however you have a lot of delay as well. Then since you have to design your system stable, that's why you have to resolve the issue of the delay. That's why in that case, if you have a lot of delay over there, then you have to sacrifice certain amount of your objective function, and then you have to try to minimize your delay. That's why in that case, you will ignore certain amount of your objective, and then you will try to minimize your delays. But suppose that you have no delay in that case. So in that case, you don't need to think about delay anymore. That's why you need to focus on your main objective function. That's why you need to improve your quality. That's why, lastly, if you have trade-off between your utility and delay, then you need to focus on your delay. You need to focus on you need to observe delay as well, and then based on the delay amounts, you can control the you can control for the utility maximization. Okay, so let me explain more about Lyapunov optimization from next slide. Okay, so here, as I told you before, we can observe the trade-off between the quality and the number of chunks. That's why, and delay as well. That's why we are designing everything with Lyapunov optimization. Okay. Because I mentioned the Lyapunov optimization in previous slide, from now on, let me briefly explain what is the Lyapunov control and Lyapunov optimization from here. Okay, so from now, for 5 to 10 pages, I would like to basically introduce what is the Lyapunov optimization. So here, when you solve some questions, your problem solving will be utility maximization. If you want to pursue energy consumption minimization, then that is your utility. Okay. Then if you want to pursue quality maximization, as we discussed up to now, then utility will be video quality. That's why always we want to maximize our utility. So in order to achieve our goal, we are using optimization techniques. Sometimes we are using linear programming, sometimes we are using convex programming. Okay, but in general optimization techniques, we have no consideration on time. So our question is that what if our optimal solution introduces delays? So in this case, we can say that that is harmful for real-time mobile systems, because every single time we want to select our decision, and then that is optimal. They should be optimal in terms of utility maximization. So every single time you will select that decision. However, suppose that you will introduce a lot of delays. Then in that case, our system will experience a lot of delays. That's why if we have trade-off between our optimal solution and delays, then what we're gonna do? So here in that case, we have to consider the time in our optimization process. So as you can see in the middle, in the letter character, so this is the optimization technique we can use when we observe trade-off between utility and delays. So our first step is time modeling. Okay, the time modeling can be done with the queue. Okay, if we have a lot of delays, then the queue will have a lot of arrival process, then the queue will increase. That's why the time can be modeled with the queue. And then so given the queue values, we can do the formulation with the Lyapunov drift then we can formulate the delays. Then we can do the optimization subject to Q stability because we already formulate the time with Q with reaction of drift. Okay. So as I told you before, we can use this technique when we observe the trade-off between the delay and utility. Okay, the delay can be formulated as Q. That's why we are saying that this is Q-based model. And then, as you can see, right-hand side, utility can be energy. If you want to minimize the energy consumption, then our utility will be energy. If you want to maximize the quality, then we can say that our utility is quality, and we want to maximize the quality streaming. Okay. And then PSNR can be another utility. So PSNR means peak signal to noise ratio, which is kinds of index represent the quality of videos. That's why you want to minimize, you want to maximize the PSNR. Lastly, if you are thinking about the deep learning platform, then you want to maximize the accuracy of the deep learning. That's why accuracy can be another utility. Okay, so when you look at this one, when you observe the trade-off between delay and utility, then you can use the reaction of optimization. So in order to better understanding, in order to make better understanding, let me give you some example. Suppose that we have a smartphone. So you guys have smartphone already. So you are doing some touch on top of your smartphone screen, and then you will execute something. You can use Kakao, you can use Facebook, you can use YouTube, and so forth. Then as you can see in the right hand side in the arrival process A of T. So if you touch some screens, then you're gonna make a lot of tasks. That's why the task generation is random. The task will be in the queue. That's why within a smartphone you have task queue. So in the task queue, in the middle, Q of T, you have arrival process that is random because that is by human being. And the departure process is depending on the core location. So suppose that you have one processor, it has several cores. So if you are activating more and more cores, then that will process the task faster. So that is good in terms of the stability. However, it's not good in terms of the energy consumption because when you activate more and more cores, you will consume more and more energies. That's why that's not good in terms of the energy consumption. So on the other hand, suppose that you are allocating less amount of cores. So in that case, your core location is very small. That's why you will save a lot of energy. That is good for mobile system, such as your smartphone. However, you only allocate a small number of cores. That's why your stability is not that good. That's why it's not good in terms of the stability. So as you can see, as you can see in this example, you can see the trade-off between the energy consumption and the stability. Okay, that's why when you want to do time average energy consumption minimization subject to stability, then you have to use the reaction of control. So in the reaction of control, if you have less amount of task in a queue, then you have some time margin. So you have enough time. That's why you can pursue your objective function, that is energy consumption minimization. However, if you have a lot of tasks in a queue, it means that you need to focus on the stability rather than the objective function, energy consumption minimization. Okay, that's why you need to speed up the processing from the queue. That's why you have to allocate more and more cores, even though it will introduce a lot of energy consumption. So you can make a dynamic decision depending on the queue bank node size. Okay, that's the main concept of reaction of optimization. So that can be formulated as follows. So as you can see in the left top side, we have some optimization framework. So we want to minimize y sub 0. So y sub 0 means the objective function, and then it has bar on top of y sub 0, which means that is time average. Okay, so you want to minimize the objective function in this case, and then you have one constraint that's called Q stability. So it means that you want to minimize or maximize or optimize your objective function. However, you have to keep in mind that your main constraint is Q stability. Okay, so as I told you before, Q stability can be formulated by reaction of drift. That's why you have to model the Q based on that. Okay, and then with some constant gap approximation, these kinds of optimization can be reproduced as follows. So as you can see in the yellow box, so you have v dot y sub 0 of alpha of t plus q of t and a of alpha of t minus b of alpha of t. So I will gonna introduce more about this equation in next slide. So as you can see in this slide, you want to minimize the right hand side. Okay, so red box means objective function. So if you are thinking about the mobile system or co-location, and then that aims at the time average energy consumption minimization, then your objective function will be energy consumption minimization. So in that case, y sub 0 will be energy consumption. So here, alpha of t means your control action. So it can be the number of cores that is allocated in our example. So in that case, that can be 0, which means that you have no core allocation. Or that can be 10, then it means that you are allocating 10 number of cores. So alpha of t means that your decision criteria at time t. So right hand side, so in gold boxes, Q of t is our observation. We have to observe how many tasks are in our queue. That's why that is our observation. So in addition to that, you have to control alpha A of alpha t or B of alpha t. So in our smartphone example, our arrival is random. That's why that is not controllable. Okay, but we can control the departure process B of alpha of t because that is associated with number of cores. Those are located at time t. So as you can see below, the left hand side, the objective function, that is our utility. Okay. So right hand side, so since that is related to Q background size, our observation, that's why that is associated with our stability. So maybe you cannot understand this fully at this moment, but let me give you some intuition based on some examples. Okay. Suppose that our delay, our system has a lot of delay. So in our task queue, we have a lot of tasks. So then it means that alpha q of t will be infinite. That's why in our equation, in the middle, q of t will be infinite. Then relatively left-hand side, the objective function should be ignored because it is very small, because q of t is very big. So in that case, we have to minimize the entire equation. As you can see in the leftmost side in our yellow box, that's why the A should be minimized because then we can minimize the entire equation. Or B of alpha t should be maximized because we have negative in front of the B. That's why this is our base operation. But semantically this is true because if the system has a lot of delays, which means that queue is almost empty, then we have to reduce the amount of arrivals as well as we have to speed up the departure. That's why as you can see here, if the arrival A of alpha of t is controllable, then it should be minimized in order to minimize the arrivals into the queue. On the other hand, if the departure is controllable, B of alpha of t, then we have to speed up the departure in order to stabilize the queue. That's why it should be maximized, as you can see in the black box. Okay, that's why semantically this is actually absolutely true. Okay, so let's think about the other case. Suppose that the queue is empty. Okay, then in the equation in the middle, q of t becomes 0. That's why right hand side should be eliminated. All the gold boxes will be eliminated because they are multiplied with 0 value. Okay, then you only have objective function. That's why you have to do the object function minimization or utility function maximization. Okay, so in this case, we have to focus on our main objective, that is utility maximization, which is minimizing the objective function in this equation. Okay, so now you understand Lyapunov framework with this example. Okay, so more details about the Lyapunov control is described in this textbook. So if you have any interest in this one, please read this one. Okay. In addition to that, you observe the v value in front of the objective function. If you have a larger v value, which means that you will put more weight on top of your objective function. So in this case, which is our main example in cell phone case. So in this case, if you have more and more V value, which means that you will focus on the energy consumption minimization. Okay, you want to focus on the energy consumption minimization. That's why you have to sacrifice certain amount of queuing delays. Okay, so if you have these kinds of Lyapunov optimization based algorithm, so the queue backload size will increase for the first stage. So in this graph, x-axis means time, y-axis means buffer backload. So if you spend certain amount of time, we're gonna see certain amount of backload size increasement up to here. And then from this time, the Lyapunov controller start to control the packet. Okay, that's why it is stabilized in this point. Okay. But if you allocate more and more power, maximum power here, then it means that you wanna allocate more and more cores here. That's why you will process packets a lot immediately. That's why the queue backload size is very small in this case. As you can see here, this is max power, maximum energy consumption. Okay. Here, and then if you are allocating minimum power, it means that you are allocating minimum number of cores here. So then you have less core allocation. That's why the departure process will be very slow. So in that case, you're gonna observe some increments, you're gonna observe some queue backload increasement. That's why, as you can see here, queue backload size diverges. Okay. So if you have a larger V value here, it means that you want to focus on the energy consumption minimization. That's why you have to sacrifice certain amount of stability. That's why this black curve will go up a little bit. Okay. But if V decreases, then this one goes down, because if the V decreases, you want to minimize the weight of the objective function. It means that you want to focus on the stability. That's why your Q backload size will be smaller. That's why this curve will go down. So this is talking about the impact of the V value. Okay. So let me think about the other case. This is related to our caching systems. Okay. So here, suppose that this transmitter want to send some signal to this receiver, but here those are associated with wireless link. That's why the transmitter can send data to receiver as much as the channel allows. Okay. So the mu is not controllable. Departure is not controllable because we have to send as much as the channel allows. Here, the departure is not controllable, as I mentioned before. And then arrival can be controllable, because in a video, as I told you before, we have a lot of chunk. So in each chunk, they have to go to this queue in order to be transmitted to its associated user. So here we can control the quality here. That's why we have a quality controller. So if we compress this one a lot, so in that case the size is very small. That's why the overflow of a stability of this queue is not good. Okay, it's not good. If we compress a lot, then it's good in terms of the stability. Okay. However, since we compressed a lot, when the chunk is arrived at the receiver, the satisfaction will be minimized. Okay. On the other hand, suppose that we did not compress at all, then the size of this stream or chunk will be very big. That's why it is not good in terms of the stability, because we put a lot of bits within the queue. However, once this chunk is transmitted to the receiver successfully, then user satisfaction will be very high, because we are not sacrificing any kinds of quality over there. That's why you can easily observe that video quality has trade-off between the stability, with the stability. That's why you can use the Lyapunov control in this case. So more details about this algorithm is explained in the paper below. Okay. So here we have another example. So nowadays we have a lot of interest in the computer vision platforms. Okay. So right hand side you can observe certain amount of ANN, artificial neural network framework. So you have a lot of neural networks. Okay. And then for the first one, index 0, so it has small number of hidden layers. That's why the accuracy is very low. However, since we have a small number of hidden layers, we have no or small number of matrix computation. That's why it should be very fast. In below ANN framework of N, it has a lot of hidden layers. Then we will increase the accuracy. That's why it takes high accuracy. However, we have to introduce a lot of matrix computation for each hidden layer. That's why it is very slow. It should be very slow. That's why, as you can see in the yellow boxes in the bottom, so if our neural network is low resolution, which means it has a small number of hidden layers, it's not good in terms of accuracy because we have a small number of hidden layers. However, it is very fast. That's why it's good in terms of the stability. So on the other hand, if our neural network has high resolution, which means that we have a lot of hidden layers inside there. So in that case, since we have a lot of hidden layers, our performance is very good, where the performance is running accuracy. However, it's not good in terms of the stability because it takes a lot of computation, therefore it takes a lot of time. That's why it's not good in terms of the stability. So you can easily observe the trade-off between the accuracy and time. So lastly, we can design the system which can do time average learning accuracy maximization subject to Q stability. So as you can see here, please look at the Q in the left-hand side. In the Q of T, we have random arrivals because we are not controlling the arrivals at all. But we control the departure process because when we choose ANN framework of 0, then that will process faster from the Q. But when you use the ANN framework of N, then it will process a lot. That's why it cannot process a lot because it's very slow. That's why the selection of the neural network architecture is related to the departure process of the Q. So as you can see in the next side, we have real-time optimization basic equation. So here our objective is accuracy. That's why I put the equation function name as accuracy. So in our original form, we wanted to the minimization of the objective function. But now our objective function is accuracy, and we want to maximize the objective function. In that case, in our original form, we have a plus notation in front of the Q of T. However, now our equation becomes maximization. That's why the notation in front of the Q of T becomes minus. So this is our equation, original equation. But as I told you before, in this case, the arrival is random. That's why arrival is not controllable. That's why we have to minimize the arrivals over there. We have to eliminate the arrivals. So lastly, you can see the red box below. So here, in the equation, we have a V multiplication accuracy of alpha of t plus Q of t multiplication B of alpha of t. So in order to check whether this given equation is correct or not, we can think about two different cases below. So if the Q is near empty, it means that the system is very stable. Then in this equation, since Q is empty, Q of t can be considered as 0. Then right side of this equation becomes 0. That's why we just maximize our accuracy. So that's why we have to select the neural network which has high resolution, which has more and more hidden layers. This is semantically true because if we do not have anything in the queue, then we have some time margin, or we have enough time to increase our objective function. That's why we have to select the neural network which can compute accurately even though it takes certain amount of the time. On the other hand, suppose that Q is almost infinite. So in that case, in the equation, Q of t becomes infinite. That's why left side accuracy will be ignored because they should be relatively smaller than the right side. Then we want to maximize the B of alpha of t, which means that we have to increase the processing from the Q. So in that case, we have to select the neural network which is faster. That's why we have to select the neural network which has a small number of hidden layers. That is called the low resolution neural network. That is semantically true. Suppose that your Q is almost full. So in that case, you have to speed up. That's why you need to select the neural network which is faster. That's why you can see that this equation or this result is good. So here we have another illustration that is also very similar. And then in the case, when you look at this one, our arrival can be controllable because in the queue in the middle, we have our arrival is a CCTV camera. So we have CCTV in the system, and then our departure of the queue will face the identification framework. So our face identification framework is static. That's why that is process. We have no control over there, but we can control the CCTV camera. If we increase the sampling rate, then we will have a lot of arrivals. If we reduce the sampling rate, then we have a small number of arrivals. That's why when we have low sampling rate, then in that case we have slow sampling. That's why we will miss a lot of information from there. That's why it has lower identification performance, because that's why that's not good in terms of the accuracy. However, since we reduce the sampling rate, it has low queuing delays. It has small arrivals. That's good in terms of the stability. On the other hand, suppose that we have high sampling rate, then in that case we have a small number of missing objects. That's why it's good in terms of high identification performance. However, it has a lot of arrivals. That's why it's not good in terms of the queuing delays. That's why we can observe the trade-off between low sampling rate and high sampling rate. But as you can see here, our departure is not controllable. In this case, our arrival is controllable. That's why we have to ignore B over alpha t, whereas we have to think about the control over A over alpha of t. As you can see here, so in our basic form of the equation in gray box, we can check that our departure is not controllable. That's why our final form will be below yellow box. So we have to check whether this given equation is correct. So suppose that Q is almost near empty. So in that case, in the equation, right side, Q becomes 0. Then we have to focus on our main objective function, accuracy. That's why we have to maximize the accuracy. That's why we have to increase the sampling rate. This is also semantically true. If Q is almost empty, we have some chance to increase our accuracy. That's why we have to increase our sampling rate. That is correct. On the other hand, suppose that if the Q is near overflow, which means that Q is almost infinite, then left side V accuracy will be ignored, and then we have to maximize minus A. Then we have to minimize A. So in order to minimize A, we have to slow down the sampling. That's why we have to take the low sampling rate. So this is also semantically true. Suppose that Q is almost overflow situation. So then in that case we have to slow down the arrivals. That's why we have to take the sampling rate which should be very low. Okay, then we can slow down the arrivals. So this is the basic introduction to Lyapunov optimization up to now. So from now on, we will go back to our main contents. So now I introduce what is the Lyapunov optimization. So as I presented in video streaming example, we want to maximize the time average video quality. Okay. So the streaming quality can be represented by average quality level for each chunk. Okay. So here, left-hand side in the figure, we can see a 1, 2, 3, 4, and so forth, n number of chunks. Each chunk has its own quality level, Q sub 1, Q sub 2, and so forth. Okay. So then in the right-hand side, the black box means the average streaming quality degradation. Since we are formulating the degradation of the quality, we have to minimize the degradation. Okay. So we have to determine the quality of video chunk in each chunk, and that is formulated with Markov decision process. That is the mathematical framework for sequential decision making. So nowadays there are a lot of studies about Markov decision process for deep learning. So that is also called reinforcement learning. Maybe you heard about reinforcement learning before. Reinforcement learning, nowadays that is solved by deep learning. That's why nowadays that is called deep reinforcement learning. But in this paper, we just consider the original form of reinforcement learning. That's why we are talking about the Markov decision process. So this reinforcement learning or Markov decision process, those are working as follows. So every single time they observe the status, they observe current state, and then they have to make a decision. And then the decision will update our state, and then we have to take the other action. And then again, the state will be updated, and so forth. So eventually, our main objective is that we want to achieve our goal with the maximum reward. Okay, the action taking is for maximizing our ultimate cumulative reward maximization. Okay, so Markov decision process for sequential decision making. That's why they will control the quality of each chunk every single time. Okay, so as I told you before, we are doing some Lyapunov optimization based decision making as well. So this is the entire formulation. So since we are just doing some introduction to the caching network formulation, so we don't need to worry about this equation too much. Just understand the basic concept would be enough. So the top, our main objective function is a minimization of average quality degradation, and then in green boxes, those are for avoiding playback delay. If we feel discontinuity between chunk playback, the user will get some unsatisfaction. That's why we have to avoid playback delay between consecutive chunks. Okay, so we have to control the quality and the transmission chunks number, and then that value, the transmission value should be less than equal to data rate. That's why we need the constraint that can be denoted as blue box. Lastly, we have some quality fluctuation constraint as well, because a lot of fluctuation over the chunks will be harmful in terms of user satisfaction. That's why we have these kinds of constraints in our formulation. So based on these concepts, we are doing some Lyapunov decision making. Okay, that's why. So this is the final form of the Lyapunov decision making formulation. Okay, so we have to make. We are designing this equation based on our consideration we discussed up to now. Okay, so then we can design Markov decision policies for dynamic video delivery as follows. So here, since we define our formulation with reinforcement learning, our state can be formulated as follows. Our action can be formulated as follows. Our state will be Q length, and our action will be quality and chunks amounts. Okay, so for the Markov decision process, we have observing state, those are random event, and there can be time varying channel and user mobility. So here we have to choose one of the caching node given the minimum cost that will be by Markov decision process as we discussed before. So simulation, we have two criteria. The first one is max arrival. The next one is highest quality. So max arrival, in max arrival, it chooses the caching helper whose channel is the strongest from the user, and decisions on quality and chunks amounts are made by using the proposed dynamic programming scheme, and then the scheme minimizing the average playback delay insistent. Highest quality case, it chooses the caching helper that can provide the highest quality to the user. Decisions on quality and chunks amounts are made by using the proposed dynamic programming scheme. The scheme maximizing the average video quality. That's why this is our designed algorithm. So as you can see in this result, proposed scheme reduces the playback delay at the similar level of max arrival, as you can see left-hand side. And as you can see in the right-hand side, you can observe that proposed scheme improves the quality at a smaller level of highest quality. Okay. In this result, as you can see left-hand side, as V decreases, the playback delay instance is reduced. The right-hand side, as V decreases, average video quality is decreased as well. Okay. In conclusion, so this paper proposed a dynamic video delivery policy of video files of various quality levels in the wireless caching network where the caching node distribution around the streaming user is varying. Okay, the streaming user makes decisions on caching nodes to receive the desired file, video quality, and the number of receiving chunks. The different timescales are considered for the caching nodes association and decisions on quality and the number of receiving chunks. The dynamic video delivery policy maximizes average streaming quality while limiting playback delay quality quite low. The proposed technique can adjust the trade-off between the performance of video quality and playback delay by controlling the system parameter V. So this is the end of the presentation today. So here we talked about the on-demand video streaming in wireless caching network based on the Lyapunov optimization as well as Markov decision process. The Markov decision process, with the Markov decision process, we control the quality of video sequentially by observing some status and then some uncontrollable situations. So with the Lyapunov optimization, we did time average quality maximization or minimizing or time average minimization of video quality degradation subject to stability. So we made our algorithm on top of Markov decision process and Lyapunov optimization. So thank you for listening to my presentation. And if you have any questions, please email me or let me know. Okay, thank you so much.